Hello and welcome to this course on basic data structures. The goals of this course is to teach what is a data structure and then build on that knowledge, introduce you to three data structures, namely stack, queue, and linked list. The prerequisites for this course is that you should have a little experience in programming, be it procedural programming language such as C or an object-oriented programming language like C++, Java, or etc. What you learn from this course is the concept of abstract data type and then the three data structures, stack, queue, and linked list. And along with that, you'll also learn what are the operations that you perform on these three data structures. And then you'll also learn something about the implementation aspects. Although I won't be implementing these data structures in a particular language, but as a part of exercises, you'll have to implement some of these data structures in a particular language. So this was the introduction to the course. Looking forward to see you again. The next topic that we will do is abstract data type. In this video, let us see what is an abstract data type. When you talk about abstract data type, you talk about something that models a data type. And by modeling a data type, we say that it describes the data properties and the operations that can be done on that type of data. Now, abstract data type is actually a theoretical concept. And if you want to implement an abstract data type, you should use a data structure. So a data structure is basically an implementation of an abstract data type. Now let us look at an example of an abstract data type. So you have this abstract data type of integer. We said that abstract data type basically describes the properties and the operations of that type of data. So how would you describe an integer? Well, an integer can be negative or positive. So we have positive and negative numbers as integers. And what operations can be performed on an integer? Well, you can perform addition and subtraction, you can perform multiplication as well as division. Now, abstract data types can also specify the constraints on operations. So in this case, the constraint is that you cannot divide an integer by 0. So you now know what's an abstract data type. It's something that describes the type of data, describes the properties of the data, and it describes what operations you can perform on a data. It does not talk about how to perform these operations or how to implement these operations or how to implement the properties of this data. That task is done by data structures. So we'll see about data structures in the next topic. And this video was about abstract data type. Let us understand what is a data structure in this video. In the last video, we talked about abstract data type, and then we also discussed that a data structure is something that implements an abstract data type. Now, when you talk about implementation, you always talk about organization of the data in memory in such a way that you can have easier access to that data and then you can use that data efficiently. So in a way, a data structure can be explained as a way of organizing data in such a way that it is efficient to use. Now let us take a look at an example of a data structure, an array. So if you have some programming experience, you already know what an array is. The array data structure actually implements the array abstract data type. Now, an array abstract data type specifies that the array is a collection of objects and any object can be accessed randomly. So if you have to implement an array abstract data type, then you will say that the memory allocation is continuous. In any programming language, an array is basically a collection of objects that sit beside each other in memory. So they are allocated continuously. And then for random access of an element, you provide an index-based access. So in this case, if you are talking about C language, then A0 will give you 5, A2 will give you 1, and A4 will give you 9. So based on the index, you can access an element inside the array. And then you also talk about operations in an abstract data type. So here as well, you talk about an implementation of the operation. So for an array, you can have searching and sorting as operations, and then to implement searching, you can use a particular algorithm for searching, maybe binary search, linear search, or any other search, and in case of sorting as well. So in this case, we are using bubble sort. So this was about what is a data structure. In the next lectures, we are going to dig deeper into specific data structures, starting with the stack. It is common to see chairs stacked on top of each other like the one you're seeing in the picture. So this is a stack of chairs. We have a data structure and an abstract data type known as stack, which arranges objects in a similar fashion. So let us study about stack in this video. So what is a stack? The abstract data type definition of a stack says that it is a collection of objects that are accessed from one end. So you have a collection of objects that can only be accessed from one end. In this case, the top of the stack. And there are two primitive options, one for addition and one for deletion of elements. For addition, you use the push operation, and for deletion, you use the pop operation. And there is a constraint, and it says that all the operations are done on the top of stack. So if you have to add an element, it goes from the top of stack inside the stack, and if you have to delete an element, it should always be deleted from top of the stack. That means the topmost element will get deleted. Now a stack is also called as last in first out. Why? Because the object that goes in last will be out the first. To explain it further, let us view this animation. So we have a stack of 3 elements. Now let us push this number 7 onto the stack. So it will go on top of the stack as defined by the stack abstract data type. So the number 7 that we have pushed is the last element to go inside the stack. Now what would be the element that comes out first? Well, the number that we have pushed, because you can have operations only on the top of stack. So 7, if we have to pop it, will go out. So last in and first out. Let us recap what we have studied. A stack is a collection of elements accessed only from one end. So you have only one end open. To add elements to the stack, you use the push operation. So it will add elements on top of the stack. And to delete elements from the stack, you use the pop operation, which will delete elements from the top of the stack. And stack is also known as last in first out, because the reason being that only one end is open for operations. That is why the last element to go in should be the first one to come out. So this was about the introduction to a stack. Next, we are going to dig deeper into how to perform operations on the stack, starting with the push operation. In this video, let us see how to perform a push operation on a stack. This is quite analogous to how we add a new chair on a stack of chairs. We always add a new chair on top of it. So what is a push operation on a stack in terms of computer science? Well, a push operation adds an element to a stack. And as described in the earlier lectures, elements are always added on top of the stack. So you have only one end and all the elements go from that end inside the stack. The notation to use this push operation is quite simple. You just have to say push and give the number to be pushed onto the stack. Let us now see an implementation scenario for a stack. So I have this visualization tool that I've created to explain the working of a stack. So stack can be implemented as an array, and you all know what's an array. It's basically a collection of elements which can be accessed randomly. Now how do we limit this access to just the top of the stack? How do we implement the constraint that is defined in the stack abstract data type, which is that only one end of the stack is open? So basically we declare an array of some specific size. Let us say in this case we have declared an array of 10 elements. Now in order to keep track of the top of the stack, you need to have something that points to the top of the stack. So in this case we are initializing a variable known as top, which contains the value to which the top of the stack points. In this case the stack is not initialized, so we are pointing the top of the stack to -1. You'll soon understand why this is -1. Let us try and push some elements onto the stack. So I'll push the number 23 and click the push button. As you can see, it showed you all the operations that it performed. So consider the operation this way. You have only the top as a means to access the stack. So here the top pointer is pointing to the top of stack. Right now the stack contains only one element, so it is pointing to that element. Once we insert a new element, it points to that element. So for example, if you have to insert some number, let's say 12, so this number 12 has to go in this place, A1. So for this, you need to increment the top to point to 1, and then using that pointer, you put the value into that space. So it's pretty simple. So first increment the top of stack and then store the value to the top. Again, a recap. Let's push number 45, increment the top and then put the value onto the top. Quite simple, right? Now let us suppose that you go on adding elements to the stack, and because arrays in many programming languages are of limited size, you can reach the end of the stack. That means there is no more space to add new elements. In this case, we say that there is a stack overflow. So let us go back to our visualization and let me add a few elements for you. So I have added a few elements. Let us add the last element to the stack. Let's add 45. Next, if I try to put, let's say 56 onto the top of stack, it will say that there is a stack overflow because there is no more space to store a new element. So that is why we call it a stack overflow. So that was how you perform a push operation on a stack. Next, we are going to check how do we perform the pop operation. I would suggest you to try to implement the stack push operation in C language. In this video, we will check how to perform the pop operation on a stack. In computer science, a stack pop operation corresponds to removing a chair from a stack of chairs. So what is a pop operation? So you have a stack, and pop operation removes the element only from top of the stack. And the notation for pop operation is quite simple. It is just pop, and pop function returns the value that has been popped out from the stack. Now let us see a possible implementation scenario of the pop operation. So we'll make use of the same visualization tool. I'll push some values on the stack and then we'll pop it out and see how it happens. So we have a few elements on the stack and the top is pointing to the top element. In the last video, we learned that a stack can be implemented as an array in most of the programming languages. And there is something that points to the top of the stack. In this case, it is an index of the top element. So to pop an element, the process is quite simple. Let us first see how this goes. So the process is you first remove the element from the top of the stack and then decrement the top pointer to point to the second last element, which is now the last element after the last element was removed, right? So let us see again how this works. So first you remove the element and then you decrement the top pointer. The value that has been deleted from the stack is usually returned from the function. So that was a possible implementation scenario of the pop operation. Now let's check what is a stack underflow. In many cases, when the stack is empty and then you try to pop an element, it is said that there is a stack underflow because there is nothing to pop out since the stack is empty. So let's go to our visualization and pop out all of these elements. Now there is only one element on the stack, and let's pop out that element and see what happens. Well, the value is deleted and the top pointer is decremented. Since the top pointer was pointing to 0, now it points to -1. It means that the stack is empty. Now if I try to pop an element, it cannot pop it because there's no element to pop, right? So it will show me that there is a stack underflow. So that was a quick overview of how to perform a pop operation and possible implementation scenario in terms of arrays in stacks. I recommend you to read the additional reading or exercise section of this chapter. In this video, we are going to learn about what a queue is. In computer science, the queue is very similar to the real-world queue that we have. So let us look at what exactly is a queue. So a queue is basically a collection of objects, right? Just like the real-world queue, we have a collection of people. Here we have a collection of objects that are stored in memory. And objects are always added to the back of the queue, right? For example, if you are buying a movie ticket and there is a queue of people there, so you would always go to the back of the queue. In the same way here, new objects are added to the back of the queue. And objects are removed from the front of the queue. So there are basically two primitive operations in a queue. One is addition, which is called as queue. Another is deletion, which is called as dequeue. And the notation for queuing and dequeuing is quite simple. You just write queue and pass on the number or the object that you want to queue. It adds the object to the queue. And to delete an object, you use the dequeue function, which usually returns the object that has been recently deleted from the queue. A queue is a first in, first out data structure. What does that mean? Well, it means that the object that you add to the queue first will be the one to go out of the queue first. Let us see this animation to understand this further. So you have a queue, you add elements to the back of the queue and you delete elements from the front of the queue. So let us queue in three numbers x, y, and z. When we queue x, it is the first number to go inside the queue, right? Let us add the other two numbers. So there is y and there is z. Now let's dequeue all of these three numbers one by one. So remember that x was the first element to go in the queue, and this would be the first one to go out of the queue. Why? Because we always delete elements from the front of the queue and add elements from the back of the queue. So naturally, the first one to go in would be the first one to go out of the queue. Easy, right? So let us have a quick recap of what we have learned in this video. We have learned that a queue is a collection of objects and you have two primitive operations. One is to add elements, another is to delete elements. The process of adding an element to the queue is called as queuing, and elements are added to the back of the queue. The process of deleting an element is called as dequeuing, and elements are deleted from the front of the queue. And a queue is a first in, first out structure. That means the first element to go in is the first element to go out of the queue. So that was a quick overview of what a queue is and what are its operations. Next, we would learn in detail some implementation scenarios for these two operations of the queue. Let us look at how do we add new elements to a queue in this video. So what is queuing? Well, queuing adds a new element to a queue, and it always adds the new element to the back of the queue. We have already looked at the notation of queuing. Usually functions for queuing are named as queue, and you have to pass the element that needs to be added to the queue. Let us look at a possible implementation scenario for a queue and this addition operation. So here is this interactive visualization tool wherein you can see how things happen. So this example is an array implementation of a queue. Now a queue has two sides, one is front and one is back, and you need something to keep track of those two sides. So we have pointers here, one is front pointer, another is back pointer. So basically the front element stores the index of the first element and the back pointer stores the index of the last element. Since there is nothing in this queue, these both are pointing to -1. That means the queue is empty. So let's queue the number 45. So I'll write 45 and then press the button queue. What just happened is basically the initialization of a queue and then addition of the first element. Now this seems complicated, but it's quite simple. The thing is, you need to know where does front point and where does back point. Now when you add new elements to a queue, these elements go to the back of the queue. This means that you need to increment the back pointers. So for example, if I add a number 5 to the queue, you first increment the back pointer and then store the number 5, right? Now you might be wondering, why is the value of front 0? Because initially it was pointing to -1. Well, think about the definition of this front pointer. Front pointer always points to the front of the queue, which means it points to the first element of the queue. When the queue was empty, there was nothing to be pointed at. So front was -1. When the first element is added, it is the first element as well as the last element. So it is at the front of the queue as well as at the back of the queue. Hence, when the first element is added, both front and back pointer are initialized. That means they point to that element. I hope this clears why we increment the front pointer for the first time. Now, for the subsequent additions to the queue, we won't increment the front pointer. We would always increment the back pointer. So let's take another example. Let's push in the value 9. The queue. It's quite so. So what does queuing do? It basically increments the back pointer and then stores the value where the back pointer is pointing. Now, at some point of time, the memory in the array is going to get full. So when this happens, we say that the queue is full. So when the back pointer is pointing to the last element, which is the last element in the array, actually, no new elements can be added. So hence we say that the queue is full. So I'll add a few elements to this queue and make it full, and then we'll see what happens. Now the queue is full and I'll not be able to add new elements to a queue. Now if I queue in something, it will say that the queue is full. Either you have to reset the queue or dequeue some element. But even if you dequeue or delete some elements, it won't make much difference. You will still not be able to add elements to the queue because you have reached the end of the array. So this was a quick implementation scenario for a queue and how do you perform a queuing operation. Next, we will see the dequeue operation. In this video, we are going to check how do we perform a dequeue operation on a queue and its possible implementation scenario. So what is dequeuing? Well, dequeuing removes an element from the queue. And from which end does dequeue removes that element? Well, from the front end. And the notation for dequeuing is you just have a function which is called dequeue, and it usually returns the value that has been removed from the queue. So let us see a possible implementation scenario for a dequeue operation. So this is an array visualization of a queue, and as discussed in the last video, we have two pointers. One is front and one is back. Front points to the front of the queue, that is the first element, and back points to the end of the queue, that is the last element. Now there is nothing in the queue, so front and back are storing the values -1. That means the queue is empty. Now let us fill in some values in this queue and then dequeue it. So now we have 4 elements in this queue. The front is pointing to the first element, that means front stores 0, and the back is pointing to the last element, the index of which is 3. Now for dequeuing, you always delete the element which is in the front of the queue. So here we would be concerned only with the front pointer. So let us dequeue an element. So the first step is to remove the value from the front. Now once the value is removed, you need to increment the front pointer, because once you remove the value, the front pointer is pointing to something that does not exist. So it needs to point to the front of the queue. So the next element is basically the front of the queue now. Let us do this again. You first remove the value from the front and then you increment the front pointer to point to the next element, which is now the front element of the queue. Now in typical implementations, the value that has been removed from the front of the queue is returned to whoever called that function. Okay, so that was a possible implementation scenario of a queue. Now there might be a point when a queue will be empty and you won't be able to delete anything from the queue. So such a scenario is called as obviously queue empty. Now what is the condition for the queue to be empty? Well, we know that there are no elements, but how do you determine if there are no elements? So there could be two conditions when the queue might be empty. The first one is the queue has not been initialized. And another condition could be when front pointer is greater than the back pointer. That means the front pointer has crossed the back. Now let us visualize this. So now we have just 2 elements in the queue. Let us dequeue all of them. At this point, there is only 1 element in the queue. So now if I dequeue this element, it will first remove the value, and as expected, it will then increment the front pointer, right? At this point of time, there is nothing in the queue. That is why it says that the queue is empty and you should either reset it or enqueue more elements. Now if I press dequeue again, it will say that the queue is empty. So those were the 2 conditions for a queue being empty. So that's it from my side. Next, I would suggest you to try implementing this queue in a programming language. Let us talk about linked lists in this video. So what is a linked list? Well, a linked list is a collection of objects which are linked together in a sequence. This figure is an example of a linked list. So we have a collection of 4 objects which are linked together in a sequence, which means that there is a sequence to these numbers. In other words, I can say that after the number 5, after the object 5 comes 15, then comes 1, then comes 9. Now, if you remember, an array is also a collection of objects, although the objects are not linked together. So a linked list is kind of similar to an array. We'll know the differences, but why do we need a linked list? Well, because arrays have limitations and linked lists kind of remove those limitations. So one limitation of an array is that there is a fixed size to an array. In case of linked list, there is no fixed size. Now, whenever you declare array, you have to give a size to it so that the compiler reserves that much amount of memory for your array. In case of linked list, you don't need to do this because objects are linked, and we'll see how objects are linked in the next few slides. Now, another limitation of array is that it is costly to add new elements in between. In case of linked list, we don't have such a problem. Now, what do you mean by it is costly to add new elements in between? Well, for example, if you have this array where you have 3 elements, and if you have to insert a number 3 in between these 3 elements, so if you have to insert 3 in place of 4, you need to shift down 4 and 9. So it is kind of costly to add new elements in a specific positions if there is already some element there. Now, a linked list is a collection of objects. We usually call these objects as nodes. So it is basically a collection of nodes. Now, what does a node contain? A node has 2 parts. One part is data and another part is link. We need this because we need to have some way to tell us what is the next node, who is the neighbor of a current node. So we have a node which has data and a link. Now the link points to the next node, which again has data and the link to the next node, and so on. Now you might be wondering, what does the last node point to? Well, the last node points to nothing because there's no node after that. And then we need something to go to the first node. So we have a pointer to the first node or a link to the first node, which is called as the head. So in order to get to a particular element in a linked list, you use the head, you start with the head, and then you traverse to that particular node. Now, what are the operations you perform on a linked list? Well, I just said traverse. So traversing is one of the operations you perform on a linked list. Traversing means going to a particular node. Or for example, I can say that read the value of the third node. So it would involve traversing to the third node and getting the value of that node. So how do you traverse? We'll see in the next videos. Another operation is appending a node. That means adding a node to the end of the list. Prepending a node means adding a node to the start of the list. And then there is an operation which allows us to insert a node at a particular position. And of course, deleting a node. So that was a little bit about linked list. Next, we will see how linked lists are organized in memory. Let us talk about how linked lists are organized in memory in this video. Now, before we go ahead, let us see how arrays are allocated in memory. Well, arrays are allocated continuously. When you declare an array, the compiler allocates a block of memory corresponding to the size of the array. In this case, the array is of characters and it has 6 elements. So it will have 6 elements in the memory, and the elements would be placed side by side. That means there is a continuous allocation of elements. So in this case, the address of the first element is 1000, the next would be 1001, 2, 3, and so on. In contrast, the elements of a linked list are not allocated continuously, they are allocated randomly. Now, the process of creating a linked list is a bit different. You have to create a node and then link that node to the linked list. So, for example, in this case, if I create a node, it is allocated somewhere in the memory wherever there is free space. And then it will have a link to the next node. Now, when I create another node, it will get created in another memory location. Again, the location of this node would be arbitrary. It would be chosen randomly based on wherever there is free space available. And then it would be linked to the previous node. Again, the same happens with the next node. Now we know that a linked lists node has 2 parts. One is data part and another is the linked part. What does the linked part store? Well, it stores the address of the next node. That is why we say that the link part points to the next node in the list. So the first node contains 2 parts. First part is the data part, which stores 5 in this case, and the second part stores the address of the next node. The same is the case with the second node, where the data part contains 9 and the address part or the link part contains the address of the next node. And the last node stores the number 3, and since this is the last node, it wouldn't point to any other node. That is why it points to null. And then as we need something to access the first node, we have another pointer where we call it head, which stores the address of the first node. So if you have to go to the second node, you first go to the first node, then check the link part. From that link, jump to the second node, and then you are in the second node. So to summarize, in a linked list, nodes are randomly allocated and they are linked to form a sequence. Now you might be wondering, how do we represent a node of a linked list in a programming language? So I'll give you an example of C language. A node in a C language can be represented using a structure. So the first variable is the data part and the next variable is the pointer to the next node. This variable next stores the address of the next node. So this was a little bit about how we organize a linked list in a memory. In the next coming videos, we will see how do we perform different operations on a linked list. Let us learn how to traverse a linked list in this video. So what is traversing? Well, traversing means to navigate to a node in a linked list. Now, why do we need to navigate to a node in a linked list? Well, it is because there is no random access possible in a linked list. Random access is possible only in an array, not in a linked list. So here I have a visualization of a linked list. In order to traverse this linked list, you need to start from the first node and then check the link of that node to go to the next node, and so on. When you find that there is no link to go ahead, you stop and conclude that this is the last node that we have reached. Now it's not necessary to always go to the last node. So you might have a logic where you check the value of each node and then stop when you get the desired value. Now let us see a code snippet and try to understand how this traversing mechanism works. So this code snippet is from the C language. In the last video, we saw the structure of a linked list node. So this code snippet builds on that structure. So the first step is to make a copy of the head pointer. This is needed because if we change the value in the head pointer, we mess up the pointer to the first node and then essentially lose access to the linked list. So we have made a copy of the head pointer. We call it the node pointer. Now in this case, we are traversing the list until there is no element left to traverse. Now the while statement checks whether the next pointer of the node is null or not. This is to check whether we have reached the end of the list or not. So here in this case, a pointer exists and it points to the next node. Hence, we go inside the while loop and then move our node pointer to the next node. Once you move, you can access the value of this node. Again, it will check whether the next node is present. Yes, it is present, so it will move to the next node. The same case here as well. Now we are pointing to the last node, and in this case the while loop will fail because there is no next pointer available. It means that the next pointer is basically null for the last node. Hence we conclude that we have completed traversal of this list because we have reached the last node. So this is how you traverse a linked list in a C language. Of course, inside the while loop you can add your own logic to check the value of each node that you're traversing, and then you can always arbitrarily stop at any given point. You don't need to go to the last node every time. So that was all about traversing a linked list. Next, we will see how do we append a node to a linked list. Let us understand how do we append a node to a linked list in this video. So when somebody says appending to a linked list, it means that they add a new node to the end of the list. So basically the process involves creation of a node and then pointing the last element of the list to that node. Now let us go through the algorithm of appending a node to a linked list along with a step-by-step visualization. So the first step is to create a new node. And then since this node would be the last node, we would make its next pointer as null. Because we are appending this node to the linked list, it would end up as a last node. Hence we make its next pointer as null because there would not be any node after this. Now since you need to add this node to the end of the list, you need to traverse to the last node. Remember that there is no way to randomly access an element in a linked list. Hence you need to traverse to the last node. Now once you reach the last node, you can access its next pointer. So naturally, what you would do is you would point the next pointer of the last node to the newly created node. And that's it. You're done with creating a new node and then appending it to the linked list. So let me go through it again. The process is quite simple. You create a new node, and because you want to append this node to the end of the list, you need to traverse to the last node. So you traverse to the last node and then point the last node's next pointer to the newly created node. And that is how you append a node to a linked list. Next, we would see how do we prepend a node to a list, which means adding a node at the start of the list. In this video, we'll check how to prepend a node in a linked list. So what is prepending? Well, you all know it. Prepending adds a new node to a linked list, but to the front of the linked list, not to the back. And it's quite simple. You have to first create a node, point it to the first node, and then move the head pointer to point to the newly created node, which is now the first node. Let us make this understanding more clear by going through this algorithm. So there are just 3 steps to prepend a node to a linked list. First one is to create a new node. When you create a node, you will have a data part and a link part. Now, since we are prepending a new node, we need to point that new node to the first node so that the new node becomes the first node. Now the next step is to move the head from pointing to the first node to the newly created node. Right? Because head always points to the first node. Right? That is the entry point of the linked list. You can only enter, or you can only start traversing the linked list from the head node. And that's it. You have prepended a node to the linked list. A quick revision. First step is to create a node. Second step is to point that node to the first node of the list so that you linked your newly created node to the linked list. And then since the newly created node is the first node now, you need to move the head pointer to point to the first node. And that is how you prepend a node to a linked list. The next video would be about addition of a node at a specific position in a linked list. In this video, we'll be checking how do we add a new node at a particular position in a linked list. So we have to add a new node at a position specified by an index, and the node can be added at an arbitrary position. So in this case, I want to add a node at position number 3, but there is already an element present at position number 3, which is 1. So how do you manage to add a new element without disturbing the linked list? So basically the goal is to make changes in such a way that this element 15 points to 6 and 6 points to 1, thereby ensuring the continuity of the linked list. So let us try to see and visualize how this process can happen. So we want to insert a node at position number 4. So the position number 4 would be 1, 2, 3, and 4. So in place of 2, we need to have a new node, and 2 should be shifted to the right hand side. So the first step is to traverse to the desired node. In this case, it would be 8, because you need to go to a node after which the new node is to be added. So since it is specified that the new node should be put at position number 4, it means that it should come after this node 8. So hence we go till the node 8. That means we traverse till the node 8, and then the next step is to create the new node. Now our goal is to point 8 to 7 and then point 7 to 2. How do you do it? Well, you already know the address of this node 2, which is pointed by this node 8. So basically you can just use this link and then link this node 7 to 2. Now 7 is connected to node 2. Now next we need to point 8 to 7, thereby connecting 8 and 7. So you now have inserted the node 7 at position number 4, and you have also ensured that the linked list is continuous. You have not broken the linked list. So this is a possible algorithm which can be followed in order to add elements at an arbitrary position. So that is how you add a new node to a linked list at a given arbitrary position. The next video will be about deleting a node from a linked list. Let us talk about deletion of a node in a linked list. So most of the times deleting a node involves deleting a node from a specific position. For example, if you want to delete the node at position number 3, in this case the node with value 1, so you need a way to make the node with value 15 link with the node with value 9, thereby skipping the node with value 1, right? Let us see how do we do this in detail. In this example, we will delete the node at position number 3, which means that we will delete the node with the value 8. So the first step is to traverse till the preceding node. Why do we need to travel to the preceding node? Well, that is where we need to do the modifications, right? We need to point the preceding node to the neighbor of the node that has been deleted, right? Essentially, we need to skip pointing to node with value 8. So what we do is we skip that node to be deleted and then point the next pointer of the preceding node to the neighbor of the node that has been deleted. This can be done with this statement. If the preceding node is n, then you can say that n.next is equal to n.next.next, which essentially means that the next pointer of the node n, in this case this node n with the value 9, is equal to the next of the next node. So next of n is 8 and next of 8 is 2. So therefore 9's next would now be 2 after this statement. So now we have deleted the node at position number 3. Easy, right? Now what if you have to delete the head node? How would you do it? Head node is the first node. Well, it's quite simple. You just move the head pointer to point to the next node. So this statement will do the same thing. If you write head equals to head.next, it means that head will shift to pointing to the next element. So deleting an element is quite easy in a linked list. Now there are a lot of advantages of linked list. In fact, you can implement stack and queue data structures using the linked list. So I would suggest you to try that out.
Hello, this is Chan Sheikh, and today we are going to code program for singly linked list. Now, singly linked list is a list of nodes, and in a node there are two parts. First part is an info part where we store the data. The second part is the link part. This is address to some other node. This can be address to some other node. And if the address part is null, means this node is not pointing to some other node. Means the link part of this node is not pointing to some other node. Means this is the last node. Now, the node which points the first node is called the start node. So this is our singly linked list. Now how to implement this programmatically, we will check it now. Now this link list can be represented programmatically with the help of this kind of structure. In this structure we have an info part which will store the information of a particular node in this variable, and the link part of a node is of struct type, as the link is for a node and node is represented by this structure, so we are declaring is as struct node star link. Means the address inside this variable will be of type node, and this is the global variable start which will always point to the first node in the linked list. Initially, when we write this fragment of code, we declare or we initialize this pointer as null in our main function. And we also create few functions like create function, display function or insert function, so that we can perform actions like create linked list or insert a particular node in the list or delete some particular node from the list, and many more operations. We will look into these operations in this lecture. So our create function need to do the thing like this. Initially the start will point to null. We want a single node need to be inserted into our linked list. So for this we will have to create a temp node where we will copy our info or our data into the info part of the list. We will make the link part of this temp node as null, and we will copy the address of this temp node to start. Now this is how this create function look like. We are firstly initializing a temp variable which is a temp node. We are allocating space so that this temp node can be created using this malloc statement, means allocating the memory space so that this node can be created, and the address of this node is copied to this variable temp which is of node star temp. Then if start equal to null, means if we are creating the first node, then copy the data part into the info part of the node. Means we have info part in our temp node. We will copy the data which we have received from the user into this node. So the data is copied to the info part of the node. The link will be overwritten by a value null, as this is the first and also the last node of the linked list, and we will copy the address of temp into the special pointer start, and we will print this message list created, and our function will exit. So we have this temp node where we have this info part, the link part. We will copy data into this info part, and the link will be null, and the address of this will be copied to start. Simple enough. Now what this display function will do, this will display the content of every node till it reaches the last node. And how can we find that we have reached the last node? It's very simple. We will simply scan the link part of the node, and if it turns out to be null, then we will stop printing the content of node. This is how we will code this display function. Now let us code this program with only these two functions. Later on we will code many more functions as well. In the display function, what we are doing, as we know that start is the address of first node, then we will copy the content of start into a pointer, say ptr. Then we will scan whether this node which the ptr is pointing is the last node or not. If the link part of ptr is not null, then we will print the info part and increment the pointer. Means we will increment the pointer to point the next node. For pointing the next node, we will simply write ptr equal to ptr dot link. So the ptr will increment. Now we will print the info part of this node. Then we will check whether the link part of this node is null or not. If not, we will increment the pointer again, and then now as we know that the link part of this node is null, our program or this function should exit after displaying the info part of all these nodes. This is a task which need to be performed by this display function. So this is the display function where we are declaring a pointer ptr and then copying the content of start into this function, into this pointer. If start is null, means the list is empty, we can't display any content, then we will simply display this message and return. Else we will iterate till we reach the end of list, means ptr is not equal to null, and in every iteration we will print the info part and then increase the pointer by this statement ptr equal to ptr dot link. Then we will print this message end of list, and then we will exit. The system as a string cls is equivalent to clr_scr. So this is the code of single linked list, or we can say a fragment of code of single linked list, where we just having two functions, create and display. In create function we can simply create a single node, means we can initialize the node or initialize the linked list. This is the structure of the node. Now in main function we have nothing but a menu driven system, where accordingly the option selected by the user we will call function. Say 1 for create list, 2 for display list, and 3 to exit from the program. This is the create list code which we have seen, and this is the display linked list code. So let us run this program. So we are creating the list, say the data is 45, list created, and when we display the list it's 45, then end of list. So our program is working fine. Now we will code furthermore, means more functions. Now we will check the functions for insertion. Now insertion can be in 3 locations. First location can be in the beginning, second location can be at the end, third location at some specified position. If we want to insert in beginning, then start need to be start pointing to this temp node, and the address of this node need to be start pointing to the first node. This will be insertion at beginning. If we want to insert into end of the linked list, then we will create a temp node, then we will overwrite this null by the address of this node, and then we will write null to this node. If we want to insert a node, say between the node number 1 and 2, we need to take a temp node. Then in this address part, the address of the second node need to be there, and its address is in here. So we will copy this content here, then this will start pointing to this node, and the address of the link of first node need to be pointing to this temp node. So if we can do this programmatically, then we can programmatically insert a temp node in any specified location as well. Firstly, we will code this function, means insertion at the end, and then we will also modify our create function so that at one shot we can create multiple nodes using this function, means insertion at end. Let's code it. For coding a function for inserting at the end of a linked list, firstly we have to reach till the end of this linked list. For doing this, we will start traversing till the end of linked list, then we will insert a new node at the end of this list, and we will simply overwrite this null by the address of this new node, and we will write null to this new node. This is the code for it. We are simply having a pointer ptr. We are copying the content of start into the ptr till we reaches the end of the list, means the ptr's link is not equal to null. We are simply traversing. If we reaches it, we are breaking this while loop. While means this infinite while loop. Once we are at the end of the list, then we are simply allocating memory for a temp node. Then in this temp node we are copying the data which we are taking as a parameter inside this function, which can be a user input as well, writing a null to this temp node, and at last we are copying the address of this temp node into this ptr. Our insertion at the end will be working fine with this fragment of code. Means this is a simple fragment of code for this insertion at the end. So this is our program where we have these three functions: create function, display function, and insert function. And this is our code. I will show how the functions are working, but let us run this program first. So this program is running. In the create function, I made few changes. Now this function will ask you that enter the number of nodes need to be created. Now say I have inputted 4. In node 0, we have 1, 2, 3, then 4. Then the node 0 contains the data 1, node 1 contains the data 2, node 2 contains the data 3, and the node 3 contains the data 4. Okay, list created. When we display this list, it is 1, 2, 3, 4, and then end of list. Program is working. If we want to insert, we can insert at the end of list as well. So we are inserting at end. Say the value is 23. If we try to display the content is 1, 2, 3, 4, and 23. So the program is working. Now we will exit from this program and try to understand the mechanism. Now this is our code. Firstly, I have made changes in the create function where I'm simply running a loop number of times, and this number is how many nodes we want to create. First time when the start will be null, we will be using this mechanism which I made you understand earlier as well. That info part, we will copy the data element, we will write null to the link part of the temp node, and then we will copy the address of temp to the start node. If the start is not null, means the first node is been created, then we will ask what is the data for this node. We will pass this variable to insert at the end function. Now this function will insert the particular node to the end of the node. So this is the very easy mechanism by which we will achieve multiple node creation at one shot. This is the display function, and this is the insert at the end function, where we are simply running an infinite loop so that our pointer gets to at the end of the node, and at the end of the node we are creating a temp node. In the temp node we are copying the data into the info part. The link part need to be overwritten by the value null, and the link part of PTR means the last node's link part need to be overwritten from null to this address of this temp node. So the program will work. Now let us code for the functions like insert at beginning and insert at a specified position. Now we will try to understand how to insert node at the beginning. So we will simply take a temp node. We will copy the content of start in the link part of this temp node. So this temp node will start pointing this first node, right? Then we will copy the address of this temp node into this start pointer. Then start will start pointing to this temp node. So by doing this we can achieve this insertion at the beginning of the list. This is the very simple and very small fragment of code. We are simply creating a temp node. This is temp node. Then we are allocating the memory for it. Then we are copying the data into the info part. Then the link part is overwritten by the value of start, means this link will start pointing to the first node, and at last the address of temp node is copied to this start pointer. Very simple. Now say this is a linked list with node number 0, 1, 2 and 3, and 3 the link path is null. We want to insert a new node here. So what we will do, we will take a temp node, we will copy the address of this second node, but this address is present in the link part of first node. So we will copy the link part of the previous node, that is the first node, into the link part of the temp node. So this will start pointing to the second node. Next, the link part of the first node need to be pointing this temp node. So we will copy the address of this temp node here. So what will be the case now? This will start pointing this, and this will start pointing this. So we will be able to insert a new node in the specified location. Let's check the code. So in this function we are receiving the data part and the position part. We are creating a temp node, a pointer. We will copy the content of start to this ptr and run this loop so that our pointer get till this position, means our pointer will be here, after which we will insert this node. So by executing this loop we will get into that specified location. If say by executing this loop we reaches that ptr equal to null, means we reached the end of list, then we will simply print this message invalid position entered. If this is not the case, we will simply increase the pointer. Now if ptr's link part, means the position entered is this 3 and its link part is null, then we are simply calling which function? Insert at the end. Our work will be done. So if the ptr's link part is equal to null, then we will call insert at end function. If not, if say the case is like this, that we have entered the position say 1 and we want to insert a new node between 1 and 2, then this else part will get executed. We will create a temp node, we will write the data into the info part of this temp node, and then we will write the ptr's link part into the temp node's link part. What is the case? This is ptr. So ptr's link part, which is containing the address of next node, will be copied in here by executing this statement. Okay, so the temp node's link part will be overwritten by the address of the next node, means ptr's link part. At last we will copy the address of this temp node to the ptr's link part. ptr's link part need to be copied by the temp node's address. So this will be the case. This will start pointing the new node, that is the temp node, and the link of this temp node will start pointing to the next node. This is how insertion at specified position can be achieved. So this is our program. with functions like create function, display function, insert at end, insert at beginning, insert at a specified location. Later we will also code functions like delete for searching data, for reversing the linked list in next lecture. We have seen the create, display, insert at the end functions. These are functions like insert at the beginning, insert at specified position. Let's now check this program. So firstly we are creating a linked list, say with 4 elements, like 1, 2, 3, 4 are the data elements. Now we are simply displaying it. The list is having 4 nodes with data as 1, 2, 3 and 4. Now we will check the insert functions whether they are working good or not. Inserting at beginning, say the data is 0. Displaying it, so the function is working. Now we will again insert into this linked list, say at the end. We are inserting the value 5. We are displaying it now. So it's 0, 1, 2, 3, 4, 5. Now I want to insert an element between this 2 and 3. So the position is second. So we will insert this at a specified location. Data is say 56. Position is second. Then we will display it's 0, 1, 2, then 56, 3, 4, 5, then end of list. At last we are exiting. Soon we will code the rest of functions in next lecture. Thank you very much.
Hey friends, today we will check the concept of deletion of the node from the beginning. In this case, if we consider that the linked list has only 3 nodes, node with data 1, 5 and 3, then our target is to delete the node with data 1. Alright, now how to delete it? Now the concept is real simple. We want start to point to the second node, not the first node, and finally we want to delete this one. Alright, simple enough. Let us summarize it once more. Start is pointing to the first node. We don't want that. We want start to point to the second node, and later we want to delete the first node. Very simple. Now in order to do this, what we need to do? We need first the address of second node, because we want the start to point to the second node. And second thing we want to do is to delete the first node. And in order to delete the first node, we would require the address of the first node. So how we can achieve this? First would be to take a temporary variable, for example ptr. Now in this temporary variable, what we will do is we will copy start. Now why we will copy start? Because we would require the address which is currently in start to delete, or in other words to free up the memory which is allocated by the node with data 1. Simple enough. And the second thing what we will do is, as the link part of this node contains the address of this node 2, we would copy the link part of node 1 to start. Now what would be the result? Let me clarify. The result would be if I copy the link part of first node to start, the link part of the first node contains the address of second, then obviously start will start pointing to the second node. I hope I have made myself clear. Alright, now how we can achieve this programmatically? First step, would be to take a temporary variable, for example ptr, and in this temporary variable we need to store the value of start. So we will store the value of start to ptr. Why it would be required? Because the value of start would get replaced, and later on we would require this address to free up or to delete the first node. Second step would be to replace the value of start. So what we will do is we will replace start with obviously link of this part. Okay, so we will replace and copy start to the link part of the first node. How we will do that? We will check the program in a minute. And finally we will free up ptr. Looks simple? Yes, it is simple. Let's try to code it now. Now here is the fragment of code for deletion of node from the beginning. It's pretty simple. If we talk about this particular variable ptr is nothing but this one. What we are doing, we are simply declaring one variable star ptr, as this need to store a address location of struct node type, as we want to store the address of a node which is definitely a structure. If for example start doesn't contain anything, it's a null pointer, then there is no node in the linked list. Obviously if start equal to null, we will simply print list is empty and return. But if start is not null, what we will do, we will temporarily store the content of start inside ptr, then we will replace ptr's link to start. Now this statement will do this one. It will replace the content of start with the link part of the node. Finally we will free up ptr, this one, and obviously as a notification to the user we will tell the user that the first node is deleted, and we will return the function. I hope I have made myself clear. Thank you for watching. Hey there, today we will check how to delete a node at the end. In this case the node with value 4. So our target is to delete the node with data 4. In fact, what is the identity of this node? This node has the link part as null. Alright. So in other words, if someone asks that how we can delete it, the answer would be to null this particular node which is second last and delete this node. Looks simple? Yes, it is simple. Let's try to understand how we can do it programmatically. I will clarify it a bit. In order to delete this particular node, we would require a pointer which is pointing to this node as well as a pointer which is pointing to this node. Now why it is required two pointers? That would be a genuine question. Now the reason why we would require this is the pointer which is pointing to this particular node will use to free up this node. Alright, so we can delete this node, but the pointer which would point this particular node will be used to marking the address part of this node as null. So the access for both the nodes is required. Now try to understand how we can do the same programmatically. In order to do that, we need to take two pointers. For example, one pointer name would be pre-ptr and one pointer's name would be ptr. Alright, so one would be behind one node to the pointer ptr. So this is ptr and this would be pre-ptr. One would be PTR and one would be pre-PTR. Now what we will do, we will traverse till the PTR reaches here and pre-PTR reaches here. Once this is done, our task is simple. Let's try to understand. Once the pre-PTR is here and PTR is here, then what we will do is, we will simply mark the link part of pre-PTR as null and delete this one. Alright, let's try to do it using a program. Here is the program. Now in here, what we are doing is, firstly we are taking two pointers, which would be pre-PTR and PTR. Alright. Now, if the start equal to null, then obviously we will return by printing list is empty. Perfect. And if the start is not null, means the pointer, means the list contains data. Now what we will do is, we will initialize PTR with the link part of a start. Means the PTR will start pointing this particular first node in here. Whereas we will initialize pre-PTR as a start. Now our prime target is to traverse through the linked list to reach this particular location. Means the PTR needs to point the last node and the pre-PTR needs to point the second last node. And that's fairly straightforward. Till we reach a node with link part as obviously null. Alright. So what we will do is link part as null. Alright. Now what we will do is, we will traverse using a while loop. While PTR's link is not equal to null, increment both the pointers. How we increment? PTR's link equal to PTR and pre-PTR's link equal to pre-PTR, which is fairly straightforward. Once we have reached this optimum position, we simply need to do these two statements. We simply need to do two more things. First thing would be to mark the pointer of pre-PTR as null, which we are doing in here. Pre-PTR's link equal to null. And second would be to free up the last node. And where is the last node? The last node is the node where PTR is pointing. So we will free up PTR.